Okay, in this lecture we are going to talk about conformations of cycloalkanes. And so let's start with talking about cycloalkanes because the one thing that we know from Lewis dot structures in general chemistry was you very rarely ever wrote ring structures, at least, and got points for it. But in organic, rings are common. So let's start with looking at the stability of different types of cycloalkanes. And let's start with cyclopropane. So cyclopropane has a 3-membered ring, cyclobutane is a 4-membered ring, cyclopentane is a 5-membered ring, and then cyclohexane is a 6-membered ring. And most of what we'll do is with cyclohexane. So it turns out that cyclopropane is the least stable of these cycloalkanes, and cyclohexane is going to be the most stable. And we'll talk a little bit about why that's the case. So first of all, why is cyclopropane the least stable? And that is because it has what is called ring strain. And what do I mean by ring strain? Well, in a triangle, you have a 60-degree angle between the carbon-carbon-carbon bond angle. In a triangle, that's what it's going to be. Remember that in an sp2 hybrid, or sorry, an sp3 hybridized carbon, that the bond angles are 109.5 because that's what the orbitals of the tetrahedron are at. So if you're going to form a cyclopropane, what you need to do is you need to not perfectly head-to-head overlap the sp3 hybrid orbitals of each carbon, so they're only going to kind of sideways overlap, and what that does is that creates what is called ring strain and makes the carbon-carbon bonds much less stable. Now, for a cyclopropane ring, you'd think, well, how unstable is it? And it's not true. It's unstable, but it can still form. So there are a lot of natural products out there that have cyclopropane rings in them. I've seen structures where they've isolated compounds from, let's say, sea creatures like sea urchins or coral. In the Start Here video, I talked a little bit about Taxol, the drug, and it was isolated from the bark of the California yew tree. Well, there was a big push to find naturally occurring sort of chemotherapy or anti-tumor drugs, and so a lot of pieces of coral were gotten, little sea creatures. Unfortunately for the sea creatures, you got to blend them up to get the compounds out of them. And I remember seeing one at one point where there were cyclopropane rings all kind of attached together. So these do exist in natural compounds, but they're the least stable of all of the ring systems. Cyclobutane is a little bit better. You got 90-degree bond angle and a square. That's getting closer to 109.5. A cyclopentane ring would be 105.5 or 105 degrees in a pentagon. That's pretty close to 109.5. So 5-membered rings are very common, and these you'll often see in steroid molecules. You'll see a 5-membered ring. And then finally, the 6-membered ring. When we get to a 6-membered ring, we'll talk a little bit about its stability. But just to go back here for the cyclopropane and butane, cyclobutane has an issue of that it has to be puckered, and that's with a P. It has to be a little bit puckered because the hydrogens will eclipse each other. So it's not a perfectly flat ring. In a cyclopentane, the puckering occurs a lot more pronounced, and you get what's sometimes called an envelope form. And that's actually going to exist in a cyclohexane. So here is a cyclohexane molecule with a 6-membered ring. Now the problem with cyclohexanes is that it looks like it might be the least stable of all. So if I took a cyclohexane ring and I thought about this bond angle of being 120 degrees, well, that doesn't match up very well at all with a 109.5 degree bond angle that you would have for an sp3 hybridized carbon. But instead what happens is that we haven't overshot the bond angle. Instead, this ring also puckers. And this shows you an example of what is called the cyclohexane chair conformation. So this is a cyclohexane chair. So instead of having all of the carbons planar, which would lead to this 120 degree bond angle, we bring one carbon down and we bring one carbon up out of the plane, and that gives us this chair conformation, kind of like a sort of like a chaise lounge type of a chair, and that allows the bonds to assume 109.5 perfect bond angle for a tetrahedron. And so the chair conformation of cyclohexane, and this is this is called a chair conformation. The chair conformation of cyclohexane makes the cyclohexane molecule the most stable of all the conformations. And we'll come back to this structure in a minute. Now, if you notice these hydrogen positions in this cyclohexane, there are two distinctive kinds of positions. Number one, there are the blue positions and there are the yellow positions. Or what are those? Well, the blue positions, and I'm going to go ahead and pull up a highlighter here. The blue positions are roughly in the plane, or roughly perpendicular to. So if we look at this cyclohexane, there are two different positions. And we're going to start with these blue and yellow positions. Now, these blue dots all represent hydrogens that are above the plane of the ring. And so these are all hydrogens that, if the ring was flat, they all are above the plane of the ring. The yellows are all below the plane of the ring. And so you'll notice that there are 6 positions above and 6 positions below the plane of the ring for those hydrogens. And again, if I go back here, here are my hydrogens, and then I'm superimposing those colors on top of them. So there's 6 positions above, 6 positions below. If we look at those positions, though, there are some positions that are roughly perpendicular to the ring, and those are the yellow positions here that are vertical. And then there are hydrogen positions that are roughly parallel to the ring, and those are here in red. And they basically, with the exception of this one and this one, they are, you can clearly see that they're parallel to the ring. So these positions that are perpendicular to the ring are called axial positions. And the positions that are parallel to the ring are called the equatorial positions. So equatorial positions are roughly in the plane of the ring. Axial positions are perpendicular to the ring. So we can map those out a little bit easier if we take them one at a time. So here, in the blue here, these are the positions that are equatorial. And again, they're roughly parallel to the ring. Here are the positions that are axial, that are perpendicular to the ring. And then when we put those together, we have basically all of the positions of the cyclohexane ring. Each carbon will have one axial position and one equatorial position. Now, it will also have, each carbon will have one position that is above the plane of the ring and one position that is below the plane of the ring. So we'll come back to that in a moment. One of the things that happens in a cyclohexane ring is that it undergoes a process which is called ring flipping. Now, ring flipping is kind of a misnomer. I'm not flipping per se anything. I'm not actually rotating. I'm not flipping upside down the ring. Instead, a ring flip is when you grab, for instance, you would grab this carbon and you would rotate it up to go into the position above basically this plane of 4 carbons. And so when you do that, you would end up with that carbon now above the plane. And the other carbon, if it remains unchanged, would also be above the plane. So this leads to, because this is rotation around a single bond, this is a conformation, and this conformation is called the boat conformation. The boat conformation would basically kind of look like this if I sketched it out. It really should be called like the canoe conformation, because that's what it looks more like. So this is a very unstable conformation for cyclohexane because these two hydrogens right here are very close in space, and these are called the flagpole positions, and these hydrogens being very close together are going to be, again, those are clouds of electron density. They're going to be repelling each other. And so the boat conformation of a cyclohexane is the least stable conformation. Here's a space-filling model showing you the flagpole positions. So this is just step 1 in the ring flip, is to move this carbon up into this position. Then, in order to complete the ring flip, we would move the back carbon. So this is just one more view right here. If I look down this, basically this plane, I would see the 2 CH2 groups that are here and here. Those you can see are those are in the flagpole positions. Those are the 2 carbons of the boat. Now, one other thing I will point out here is, notice all of the other hydrogen pairs here. How would I describe those? I would describe those as being eclipsed. So the boat conformation has 2 negative things going for it: the interaction between the flagpole positions and the eclipsing hydrogens. Okay, so that's a significant problem. To complete the ring flip, I'm going to grab now the other carbon and I'm going to move it down. And so when I move that down, I'm going to complete my ring flip. So this is what my ring flip would look like. I'm going to bring this carbon up into the boat, bring this carbon down, and so these 2 positions right here, this is what constitutes a ring flip. So if this was carbon 1, 2, 3, 4, 5, and 6, this would be carbon 1, 2, 3, 4, 5, and 6. Okay. Now, a ring flip, by doing this, what it does is it interchanges the axial and the equatorial positions. So notice right here, this pink position on carbon 2, when we do the ring flip, that pink position on carbon 2 goes from being axial up here to being equatorial down here. What didn't change about that pink position? It is still above the plane of the ring in both conformations. So if we looked at this blue position right here, attached to carbon 1, that is this position here, it went from being equatorial to being axial, but it is still the position that is above the plane of the ring in both of those chair conformations. So a ring flip causes the axial and equatorial positions to interchange in the cyclohexane ring, but it does not cause above the plane of the ring positions to change. They are still above the plane of the ring. Okay? So that's what a ring flip is called and how it works. So again, this shows you the carbons, and it shows you the interchange of the axial above to now being above but equatorial. Now the energy barrier for this, and when I wrote these slides, and these slides are 20-some years old actually, but they do their job, everything was done in kilocalories per mole. So basically what you have is, to do a ring flip, it takes about 11 kilocalories per mole. And the thermal energy at room temperature is about 20 kilocalories per mole. So cyclohexane molecules are constantly ring flipping in real life. If you were able to stop them, you would see that. So that is the ring flipping process to form the different conformations of the cyclohexane ring. Now, if we put a substituent on that ring, like a methyl group, the methyl group could be axial, and when this undergoes a ring flip, it would then become equatorial. Now, the most stable conformation, because these two conformations now have different energies, and it turns out that the equatorial position of the methyl group, when it is in its equatorial position, it is the most stable conformation, whereas when the methyl group is in the axial position, this is the least stable of the conformations. And so the most stable conformation of a substituted cyclohexane is always the one where the largest alkyl group is equatorial. And it would be best if all the alkyl groups were equatorial, but that's sometimes not possible, as we'll see here in a few minutes. So the question is, why is the axial, having an alkyl group axial, more unstable than having it equatorial? Well, that has to do with what the methyl group is going to interact with. And these interactions are destabilizing interactions. So these are what are called 1,3 diaxial interactions. They're diaxial because it occurs between the groups on the same side of the ring that are axial to each other. And they are at the relative positions of 1 and 3. So these are called 1,3 diaxial interactions. And they are the destabilizing interactions between in cyclohexanes that we are going to use to judge their energy. So you can kind of see a little bit more of that. Here's the methyl group and its size, and it is very close to these two hydrogens that are also axial. I can do a better job of that if I make the space filling model. Now you can see that the methyl group and those axial hydrogens are very close in space, and this is what is called the steric repulsion of those basically clouds of electron density. So the 1,3 diaxial interactions are destabilizing. Whereas if the methyl group was equatorial, there are no diaxial interactions. And so if I make methyl cyclohexane, what I will end up with is that the equatorial conformation is about 1.4 kilocalories per mole more stable than the diaxial one. And at some point in the two classes, we will talk about how you calculate this, but that means that basically 90 to 95% of the molecules are in the equatorial conformation, and only about 5 to 10% would be axial at any one time. And that can come about by doing some computer calculations and using the basically using the equilibrium expression and calculating an equilibrium constant delta G. So we'll talk about that at some point during the course, during Organic 1 and Organic 2 courses. Okay, so how do we analyze cyclohexanes like we did in the last lecture for Newman projections? So here's what we need to do. So let's say that I wanted you to write the 4 possible conformations for 1,2-dimethyl cyclohexane. Now, before we write that, I want to introduce the terminology of cis and trans for cycloalkane rings. And so if you have a 6-membered ring, and I'm going to draw it like this, and if you are basically, I could draw it like this. This is in biology, this would be called a Hallworth projection, and you may have seen these types of flat cyclohexanes in biology for structures of starch, for structures of sugars. They are totally incorrect. Those sugars are in a chair conformation. But humor me for a moment. If you have 2 groups that are on the same side of the ring, that is the cis conformation. If you have 2 groups that are on opposite sides of the ring, those are called trans, just like cis and trans for alkenes. However, this cis and trans, these are not conformations, because I cannot convert the cis into the trans without breaking that bond. And so it's not a simple rotation around a sigma bond. That is not the way that we do this. So cis and trans are not conformations. They are stereoisomers. Okay? So now that we have cis or trans, let me throw out one other thing. How would I represent that using bold and dashed wedges? Well, when I have a bold wedge and 2 groups on both bold wedges, or when I have 2 groups that are both on dashed wedges, those are cis. So that indicates that both of the groups are on the same side of the ring, which is cis. If I want the trans would have 1 group being on bold and 1 group being on dashed. That would be our trans conformation. Okay? So I have to introduce that because I'm going to ask you to write the 4 chair conformations for 1,2-dimethyl cyclohexane, and then we are going to rank them in energy from number 1 most stable to number 4 least stable. So the first thing I have to do is I have to get good at drawing chair conformations, and this takes practice. But let me kind of give you a little bit of an easier way to do this, or this is how most textbooks suggest starting out drawing a cyclohexane. First, you want to draw 2 parallel lines, but you don't want them to be perfectly parallel. You want them to be offset like that. And then I'm going to draw 1 form of the chair cyclohexane. So what I would do is I would take this position and draw the carbon that's above the plane of the ring, and then I would down here I would draw the position that's below the plane of the ring. So that would be the way to draw a chair conformation. If you want to reverse that process, you can do this and then draw this one above the plane of the ring, and this one then below the plane of the ring. And have I been doing this for 27, 28 years? Yes. Am I good at drawing this chair conformation? Apparently not. So this would be the ring flipped version of that chair. Because I'm right-handed, I call this the right-handed conformation and this the left-handed one. If you're left-handed, then call this one the left-handed and this one the right-handed. I'm better at one, obviously, than at the other, and you will be as well. So you just have to be able to draw one really well. And so this is the one that I just drew. Now, in terms of the positions, let's draw in the axial positions. So first of all, let's draw the positions that are above the plane of the ring that are axial, and it's those three. So this is an axial position, this is an axial position, and this is an axial position. There are three axial positions below the plane of the ring. Down, down, down. So that is also axial. This one is also axial, and this is also axial, but those are down. So let's use circles for above the plane of the ring, and let's use triangles for below the plane of the ring. And if you're a person that has one of those little bags of like colored markers and highlighters in class, you can color code this. But I have my axial positions that are above the plane of the ring and my axial positions that are below the plane of the ring. So now the equatorial positions go in roughly parallel to the ring. And the trick here is I have one more bond to put to this carbon, for instance. Let's make it look as tetrahedral as we possibly can. Okay, so it would go this way. The one here would go this way. Now notice that this one kind of went below, so that's an equatorial position. Now this axial position is above the plane of the ring, which means this equatorial position has to be below the plane of the ring. Since this axial position is below the plane of the ring, this equatorial position must be above the plane of the ring. And then I can go down the line. Axial above, equatorial below. Axial below, equatorial above. Axial above, equatorial below. Axial below, equatorial above. Okay, so what I just did here, and it'll take you some practice to be able to draw these well, is to basically draw all three axial above, all three equatorial above, and then all three axial below and all three equatorial below. Okay. So notice that the axial above and the axial below alternate as we go from carbon to carbon. Axial up, axial down. Axial up, axial down. You get the idea. And every carbon then has a position above and a position below. Okay? So there's an online quiz where you're going to identify whether the hydrogen is above or below the plane by basically drawing out or looking at this diagram. Now it's important to be able to recognize whether the bond is axial or equatorial. And it's also incredibly important to understand whether or not and recognize whether the bond is above or below the plane of the ring. Now what I'm asking you to do here is let's draw out conformations of the 1,2-dimethyl cyclohexane. So I'm going to draw my chair, and I'm going to choose two carbons as number 1 and number 2. I usually choose this upper right hand one to be number 2 or number 1, and then I choose this one to be number 2. That's just how I do it. Again, you don't mess with my system, I don't mess with your system. So you can choose any carbons you want to be number 1 and number 2 as long as they are next to each other. So for carbon number 1 here, the axial position would be up. Down for carbon number 2, the axial position would be down, and the equatorial would be here, and the equatorial would be here. And notice how that's a tetrahedron. People get themselves into trouble when they draw those 4 bonds and they don't look like they're tetrahedrons. And then basically what they've done is they've created like their own view, and I can't figure it out. And one of the things that I will tell you, and this is the first time in this course I will tell you this, that if I have to guess at an answer that you put down for a quiz or a test, I have a track record of guessing 100% wrong every time. So if you're going to force me to guess, I'm going to guess wrong every time. So the moral of that is, don't make me guess, because I'm horrible at that. And if you get the joke there, it's because I have no idea what you did. So you don't want me guessing. You don't want me guessing negative. You don't want me guessing positive. So make me see what you want me to see. Okay, I digress. Let's go back to this one. So I'm going to write out 4 of these chair conformations. And this one I'm pretty good at. And I'm going to put those positions, carbon 1, carbon 2, 1 and 2. Okay, so there's my 4 chair conformations. And so now let's put methyl groups in the possible combinations. So let's start by putting a methyl group on carbon 1 axial. And on carbon 2, let's put the methyl group in the equatorial position. And now what I'm going to do is I'm going to do a ring flip without flipping the ring. And you're like, I can't handle a semester or 2 semesters of this. Sucks to be you. What do I mean by that? What I mean by that is, remember, when you do a ring flip, what happens to the axial and the equatorial positions? They interchange. So if I'm only good at writing one of these chairs, which apparently I am only good at writing one of those chairs, then what I need to do is do a ring flip without drawing this one. So if I ring flip this molecule right here, what happens? The hydrogen in the methyl group switch from being axial and equatorial, and on carbon 2, the axial and the equatorial positions flip. So this structure, we'll call this structure A and B. B is the ring flipped, non-ring flipped A, because I interchanged the positions. Now, time for a quiz question. A and B, what are they? Are A and B cis, or are A and B trans? And they are the same. So are they cis or are they trans? So the video will stop. Tell me which one they are. Are they cis? Are they trans? Okay, to answer that question, let's dispel some mistakes that people make when they first start doing this. What does it mean to be cis and trans? Something that's cis is what? When the 2 groups are both on the same side of the ring. They're both either above or below. Now remember up here that I have axials above, but I have axials below, and I have equatorials below, and I have equatorials above. So the axial and equatorial don't necessarily tell me whether it's cis or trans. And they don't tell me that at all, actually. What tells me whether these are cis or trans? Whether they're both above, both below, or above and below. So, question, what is this methyl group, above or below? If you said above, that's correct. What about this methyl group, right here, above or below? If you said above, you are correct. What is A? A is cis. Let's go to B. What is this methyl group, above or below? If you said below, you're correct. And actually, in keeping with my system, because I don't need to mess up my own system, it would be a triangle right for being below. How about this methyl group over here? Above or below? Below. B is cis as well. So when you're identifying cyclohexanes as cis and trans, you're only looking at the positions to determine whether they're both above, both below, or one of each. Okay, so I just drew the two conformations of 1,2-dimethyl cyclohexane that are cis. So now let's do trans. So let me put a methyl group here, and let me put the hydrogen here. Here is my next question for a quiz question, video quiz question. Where should the methyl group go? Should it go in the equatorial position, or should the methyl go in the axial position to form trans? Where should it go? The methyl group, should it go axial or should it go equatorial? Okay, go ahead and answer that question. All right, what is this methyl group, above or below the plane of the ring? It is above. Where should the methyl group go to be trans? It should go below. So the methyl group should go in the axial position. So this is trans. Now let's do a non-ring flip to ring flip on the cyclohexane. So I'm just going to interchange the groups. I'm going to interchange the methyl and hydrogen. I'm going to interchange the methyl and the hydrogen. Now, if I was smarter, what I should have done is I should have asked you for this molecule, and I should have said, is this cis or trans? And of course, now you would say, well, it's trans because I need 2 trans and 2 cis. But when you look at this, can you see the fact that it is indeed trans? What is this methyl group, above or below? Below. What is this methyl group right here, above or below? Above. Trans. So when we first start looking at these cyclohexane rings, particularly the 1,2-disubstituted ones, we can run into a little bit of problems simply because when we look at that, until we get used to this and until we really take a step back and become very systematic in what we do, below, above, trans. So now I have the 2 cis's and the 2 trans. So I've got molecule A, molecule B, molecule C, and actually conformation molecule D. All right, so I've got A, B, C, and D. Well, if I give you this as a problem, I would say write the 4 chair conformations of 1,2-dimethyl cyclohexane, identify each as cis or trans, and then rank them in energy from number 1 to number 4. All right, so can we rank these 4 chair conformations in terms of what is the most stable and what is the least stable? So let's start with that. Which of those conformations, A, B, C, or D, is the most stable conformation of the 1,2-dimethyl cyclohexane. And you'll get choices A through D. Which one is most stable? Which one is least stable? Okay, how are we going to analyze that? Well, we are analyzing that with each, we're looking for destabilizing interactions. What are the destabilizing interactions? They are the 1,3 diaxial interactions. So in molecule A, how many destabilizing interactions does it have? 2. In molecule B, what does it have? Well, when the methyl group is axial below, here are the 2 axial below hydrogen positions. So it also has 2. When the group is equatorial, what happens? Nothing. There's no destabilizing interactions. Okay, how about for C? Well, C has the hydrogen above the plane of the ring has 2 destabilizing interactions, as does the methyl group below have 2 destabilizing interactions. So it has a grand total of 4 now. How about the D? D has none. So in terms of A, it's got 2 diaxial interactions. B had how many diaxial interactions? B had 2 diaxial interactions. C had 1, 2, 3, 4, and trans with the 2 methyl groups equatorial had 0. Which conformation has the least number of destabilizing interactions? D. Which one has the most number of destabilizing interactions? C. What about A and B? A and B have the same number of destabilizing interactions. 2. So these 2, A and B, would have the same energies. So in terms of ranking, D would be number 1. A would equal B at number 2. And C would be number 3. So that's how we would rank these cyclohexane, the 1,2-dimethyl cyclohexane. Now, do I have an extra slide here? Yes, good. Let's do another problem, only this time let's go ahead and do 1, 3. And let's not make the groups the same. Let's make them different. So I will always ask you to draw out the 4 chair conformations, and I will tell you what the alkyl group should be. Here is the potential problem. Let's say I wanted to do 1 ethyl, 3 isopropyl cyclohexane for this. Well, you would have to know that if this is going to be 1 and this is going to be 3, you would have to say, well, I know what an ethyl group looks like. Do I remember what an isopropyl group looks like? And this is where people get themselves in trouble because they draw the wrong alkyl group. So you gotta know you have to know your IUPAC names of the alkyl groups. Okay, so here is molecule A. Let's do a ring flip on that. The ring flip here would be to then interchange the isopropyl and the hydrogen. So there's B. And now what I want to do is now I want to actually draw the other two conformations. So why don't I keep the ethyl group like it was in A and make the isopropyl group in the same position as it was in B. And now we'll ring flip that. Right, our flipless ring flip system. Now hopefully there are two cis and two trans. So here's my question. As far as the trans goes, which of the two, which pair of chairs is trans? And your choices are, is it A and B, because we ring flip those, or is it C and D? So which one of those two is trans? Well, both of the positions would have to be, for trans, they have to be one above, one below. If I look at A here, the isopropyl group is, say it with me, above. The ethyl group is above. So actually A and B are cis, which leaves the C and D as being the trans. Okay, so I have to identify each one of these as cis or trans. So A and B are cis because they're both on the same side of the ring. A both above, B both below. C below for isopropyl, above for ethyl, and above for ethyl, or above for isopropyl, below for ethyl. Now let me take a moment here for an aside. If you're getting confused as to where the equatorial positions, whether they're above and below, use the axial positions as a guide. Okay? What do I mean by that? Is this ethyl group above or below the plane of the ring? Let's just say for the sake of argument that I go, I don't know, I forget. Let me ask the question. This carbon has to have one position above, one position below. How about this axial hydrogen? Is it above or below the plane of the ring? 99.9% of the time people will look at the axial position, they'll go definitely above. Well, if the hydrogen is definitely above, that makes the ethyl group definitely below. So use the axial positions if you're not quite sure of the equatorial positions. Because each carbon must have one axial, one equatorial, but it also must have one above and one below. Okay? So now we've got our four conformations. We've got them cis and trans, labeled cis and trans. So the last thing is, who is the most stable conformation? And who is the least stable? Let's start with most stable. Of A, B, C, and D, which one is the most stable? Go ahead and answer that question. And now go ahead and answer which one is the least stable, A, B, C, or D. All right, most stable. B. Why? Because both alkyl groups are equatorial. They lack the destabilizing interactions when they are axial. Least stable, make them both axial. That's A. Now, what's left over? What's left are C and D. C and D in this case, because the alkyl groups are different, they do not have the same energy. So, hopefully the last video quiz question, of C and D, which one is more stable? Of C or D, which one is more stable? How are we going to judge that? Well, C has the ethyl group axial, which is bad, which is the destabilizing interaction, and D has the isopropyl group axial. So each one has one group axial. How do we break the tie? Well, remember that when we were doing Newman projections, the size of the group makes a difference. So the bigger the group that was gauche, the more unstable the interaction. So in this case, the bigger the group that's axial, the more destabilizing it is. So we want the small group axial as opposed to the larger group. So what's number 2? Number 2 is C. What's number 3? Number 3 is D. So we look at the number of the destabilizing interactions, and then if we have a tie in that number, then what we like to do is then we like to say, okay, let's use the size of the groups. The bigger the group, the more destabilizing it is, and that helps us determine then which of those interactions is more destabilizing, which then tells us what the overall stability of the molecule of the cyclohexane chair in this case is. Okay, so that is analyzing cyclohexane chair conformations. There's online quizzes, both written and also multiple choice, for you to try, and plenty of practice problems. So remember the fundamentals and begin to practice your cyclohexane chair drawing abilities. Okay? All right, in the next video we will start into stereochemistry. And that is one of the most important areas of organic chemistry. So that will be the next lecture video series.